there. Well, I set up the recording. Can you all raise your hand if you can hear me? Click on the raised hand. Lets me know that you can hear me. Good. We got most everybody's raising their hands. If you can't hear me, check your own hardware because most everybody's raising their hands on this. So that's excellent. Plus you find out where the hand raising goes. And this way I can call on you and all that good stuff. Also, can you see the screen? You should see a plane, Fly to Learn logo playing on the front. So let me put your hands all down for you. Raise your hand again. Make sure you can see the screen. Okay. We got folks, hands raised. That's most excellent. Okay, great. And we're all set. All right. Well, let me click back over here. Recording. Jump back and forth. Let's get started then. This is lessons 3, part 6 and 10. We talked a little bit about 6 last time. We're going to go through that again. Go through the very first lessons for some folks that were here. Just a review of taking off and things. I won't be showing much out of the airplane, the software itself, but I'll do it with screenshots. And we're finding that the lag is just so bad when I'm running X-Plane that it looks like X-Plane's really slow when it's really the webinar software. So we've got some screenshots I can show you there. On this lesson too, we're going to concentrate enough on lessons 6 and 10. We're going to actually show the PDFs and kind of go through those in a little more detail than maybe we would on other lessons. Okay, Jeremy's got a question. Let me ask him. Hey, Jeremy. Jeremy?
Yeah, I don't have a question.
Okay, your hand's up. All right, sorry.
Sorry.
No, I'll put it down. Okay. Stick your hands up in the middle if you have questions, and we'll go through it. Okay? Now, and if it's a really detailed, heavy-duty question, I'll make sure and answer it afterwards. And if I can't answer it, I'll bring in Randy Witt, who's the other co-founder and started X-Plane from the engineering side. He is part of Laminar Research, is a part owner in there, and he can, any of the very technical questions, he can nail those. All right, now let's do a quick, let me get back over here and let's get started. All right, this is the quick flight setup screen. When you go to use this with your kids, this is a screen, it's under settings, then quick flight setup. We're going to be running almost all the time out of Lowry. We do that because it's an Innsbruck. There's big mountains on either side of the pass. It's hard for the kids to get lost, or it's less difficult to get lost. Or I should say it's more difficult to get lost, excuse me. We use the Cessna 172. You set the time to 8 if it's in the middle of the night in clear skies. All right? So that's why we use these all the time. We go to take off. We pause it. We click on the brake lights, turn those off so the brakes are off. We push the throttle in. And just remember, you're going to fly by keeping this cursor right here. If you fly it and the plane pulls to the left, you're saying, well, what's wrong? It's because it is left. Thanks to Edward here, we went back and checked. We've got software, lesson 8 software, where he says runs fine on his laptop and solves some issues we have 7. So we're getting that squared away and out to people. So if you've had issues with 7, we think 8 will work just fine for you. Thank you, Edward. All right, now, the next thing you have is where we collect data on this software, and which makes it that this is not a toy. This is actually used by people for proof of concept. I know Boeing uses it, Gulfstream tells me to use it, Burt Rutan uses it. These are all people that are designing and building airplanes. This is particularly important for the science teachers here in the fact that you're going to be teaching engineering and science in years to come in the new science standards that are emerging. They want to see that we actually model. So I had a professor, I was at a robotics conference of all things, and he said, you know what, if you aren't doing simulation before you build something, then you're not doing modern day engineering. So this is a chance for you to kind of cross those off your list of things you're supposed to cover. Okay? And then there's some data to see it. You can see it. You can actually graph it with it. So those are some of the tools we can use in FlyLearn. I'm going to kind of push this fast. We've talked about this in the past, and many of you have seen it. Okay. And then we can reduce the number of lines here by just unclicking down in this area. All right. Here we're getting to the point of now talking about flight controls, and this is in lesson 6, and stability. This is a fine lesson. If you go do the first 5 lessons and stop, that's fine. But if you want to continue, you can add this lesson. But whether you do this lesson or you stop at this point, this is a good time to build an airplane. I mentioned this last time. We got some new folks on here, but just want to show you this. This is a Jetstream. Very simple airplane. When I was a kid, they were, I think, 25 cents, 35 cents. My grandmother would always give me a quarter and run out, and we'd buy and build these things. Just loved them. And so we had the kids build it. You know, here's the stock pieces. They go out and build it. It looks like this, and it flies for a few seconds. They don't fly that long unless you got them up in the wind. Until you say to the kids, whoops, what can we do? What can we do to make this fly longer? And what the kids, if they've done mass, they've done drag, they've done thrust, and they've done lift, they're going to tell you a couple things. Well, lose the landing gear, lose the cockpit guy, cut the plastic down off the propeller so it just glues maybe that nose piece on the propeller that holds the propeller to the fuselage being the body of the airplane. All right. For those who don't, not palette people, that's cool. There's the fuselage, which I can't draw with my mouse. Really darn, I'm drawing it white there. In fact, let me go ahead and change the pen color so it'll come out a little bit better. So this area right here is the fuselage. I'm drawing with my... All right. Well, maybe you go ahead and change this so you can see this. You cut this back right here. Cut some of that off. You glue it on. The kids will come up with all those things they can do it. Well, it's a good time. So they've gone out, they've flown in 2 seconds, they come in and do all these things. But now's a good time to talk about stability and the movement of the airplane. Reason we hold now, we don't really get into this sooner, is because our real focus, again, is we're doing this to get the next generation of engineers. I thought it was a bigger priority to learn potential kinetic energy and forces and mass, because that applies to science across the board. You start getting to stability and flight controls, that's a little more plane specific. But here's the time you can before you take them back up. You can teach them pitch. That's the nose of the plane goes up and down like a boat, pitches. You can do roll, and you can do yaw. Roll, yaw is left to right, roll is rolls on the side. On these little airplanes in particular, roll is a big issue, and we can correct a lot of that by adding dihedral. And we do that by dihedrals. We're bending up the tips of the wings. So I've slid the wing out, I bent this edge of the wing up right here. Right in this area, right there. And then I glued it. On this case, what I did is I scored it. I'm using my pencil really to go through the balsa wood a little bit and then snapped it up and glued it. Then I had to slide the wing back through the fuselage, and so I could do the other tip. If you do both tips, you aren't going to get them back through the fuselage, and just one of your kids will do it. If you look on this airplane, we got rid of the landing gear. We don't have a cockpit. So we did, and in a little bit, once we've got those 2 wingtips up, from up here, we've got both wingtips up, we got a bigger motor, and now because we have a bigger motor, we have a winder. And now a plane that was flying just a few seconds, you can get a 4 to 7 second flight, which might not sound like a lot until you count to 4 to 7. You realize it's a pretty good flight. And every once in a while, my kids have built them and they've flown off, which is, the child's a little disappointed it happened, but everybody else is so fired up because that plane flies away. So that's a great cumulative activity. If that's all you're going to do, say with your 6th graders, and then 7th grade, you're going to do the engineering side, or with your 6th graders. With us, we use our 7th graders, do the flight side, the first 5 lessons, and they do this. And we actually go so far as having build Daredevil airplanes by Aero Racers. A nice stick and tissue airplane. It's pretty impressive. We'll have the 7th graders do that and stop. And then the 8th graders will go on to the next session into stability, a lot more stability. We'll talk about that, and we'll go into engineering. And some of our 7th graders go into stability because it lends itself to simple machines. Now, I just went through that pretty quickly. Does anybody have a question? Go ahead, raise your hand. I'll click on you, and we can all hear what your question is. All right, here we go, Eric. Hey, Eric, welcome from down under and the other side of the world and all that good stuff. Eric is from New Zealand, I believe. Right, Eric? Hello, Eric. I've got you unmuted. Okay, Eric, why don't you write your question? For some reason, you're not coming through. Oh, now I can hear you.
All right, can you hear me now?
Yes, sir. How are you doing?
Really good. On stability with some of the later lessons and the very short wingspans that you've got, we've had some problems with the high torque on the engine causing us to roll quite readily. Do you have any ways to manage that?
Okay. Well, when we get what we did on this model airplane and what you could do like possibly on that, and I will also get with Austin and Randy. I've not seen it on this. I've not so much seen it on the simulator maybe that you have. So I know on the model planes we put wing tips. We raise the wing tips on either side, and that corrects for a lot of the roll. On the simulator itself, I'll ask Randy. I've not seen that in lessons 7 and 8. So what, when you change the aspect ratio, you really shorten the wings down, do you have the problem, or when do you see it, Eric?
Yes, when we have the very short wings, that's correct.
Okay. I will go ahead and check on that to find out what we can do on the simulator itself. Okay? I know you could add, you could pitch a bunch of dihedral into it, but that wouldn't be very realistic. So let me ask, all right, Randy, on the simulator. You're the first one to bring that one up. Simulator lessons 7 through 9. What about correcting for that roll? Okay. All right. Anything else, Eric, for right now?
Nope, that'll do it. Thanks, Tim.
Thank you.
Tom. Yeah.
All right, we got him there. We'll find out what's going on that. I'll put his hand down, make sure there's nobody else. All right. Now, if nobody else, I'm going to move on here. Sorry. The next lesson is flight controls and stability. When Eric first saw this we really worked on this lesson plan and tried to improve it from what we were originally doing. And I think it's much better now. It was really quite long, and I don't think our results were consistent. They talk about there's roll. There's the 3 control surfaces. You can see roll. Whoops. Roll, pitch, and yaw. I'm going to go ahead and you see them right there. But what I would like to do is take us off PowerPoint. I'm going to take us into a PDF that actually is the actual lesson plan and bring it over here so we can look at that. So right now, for the time being, we're going to be off PowerPoint. I'm going to just show you the PDF. Okay. Now, this is showing the whole screen. I'll come back and check. I may lose you and have to go back out of full screen here. But, okay, there we go. This gets in the lesson right here about stability and what stability means. And he talks about a lot with the tail. We try to get the kids to see, if you see with the airplane and the arrow, that if you shoot an arrow without a tail, if there's no interference, nothing acts upon it, which is highly unlikely, the arrow would go straight. But since wind does act on it, any kind of source of drag, the arrow pretty quickly will be going sideways and going just not where you want it. So early on, human beings figured out, hey, if we put a tail on it, that feather tends to dampen that interference, and it keeps the arrow flying straight. Well, basically that's what happens in an airplane. So it dampens any of the changes to the flight plan of the overall plane. Okay? So we talk about that with the kids. Then we talk about roll, yaw, stability, and there's some dihedral shots there. That's one way to correct it. But what I really want you to get tonight, when we get started on this, is pitch stability. That's the tail moment arm and the center of gravity. Right here. I'm going to blow that up again. All right. If you look at, there's the tail moment arm. The tail moment arm is the distance between the center of lift to the tail, and that balances the center of gravity moment arm, which is from the center of lift to the center of gravity. Now, what's center of gravity? Center of gravity is, if you can imagine, I can take the airplane and balance it on my finger. That distance between the center of gravity and center of lift is the center of gravity moment arm. And then the tail moment arm, again, is from the center of lift to the tail. And just like on the teeter-totter, you're showing the fulcrum. So the fulcrum in this case is the wing. I'm willing to bet most pilots think the fulcrum is the center of gravity. And anytime you see this on aviation, they almost always just do weight and balance problems, and people will learn to do the problems, but they really don't understand what they're doing. And this didn't come from me. This came from the CFI folks that are interested in this. Okay. Now you could stop. You could stop at this point. And that, just leave it at that with them. I think it's a great time to teach moment arms. And if you've got the kids and they're doing simple machines, you're going to take them a little bit further. Some kids will get better than others, but it'll certainly prepare them for when they're taking some high school physics. And we look at the frogs over on our right here. 2-pound frog, and it's really a toad on the right, but what you say, amphibians. So 5-pound frog, 2 feet away, 10-pound toad, 1 foot away. They both have the same moments because it's their distance from and their weights acting together on a fulcrum. This is why, for the non-scientists here, that when you play the teeter-totter when the kids are little, you put them way at the end of the teeter-totter and you sit up close to the fulcrum and you both can balance it. Same thing going on here. Well, we asked them a series of questions. What about a frog that weighed 2 pounds? How far would it need to be from fulcrum that produces 10 foot-pounds of torque or moment? Well, that would need to be 5 feet away. What about a hefty 20-pound frog? How far would this need to be from the fulcrum to produce 10 foot-pounds of torque? Well, it'd have to be a half foot away. So you get a sense that we get them doing that working. Now we go back to an airplane. And we look at the center of moment, center of gravity, and we walk our way all the way through it with the kids. And for example, we say tail moment equals times the tail moment arm times the lift generated by the tail. Remember, we're not saying you necessarily have the weight of the tail alone. Usually there's lift generating, many times the lift is generated just the opposite direction that the wing lifts. Assuming most of the time lift on a wing is going straight up in the front of the airplane, the major wing. The tail, like for example on the Cessna 172, the lift is pointed down. So you got force, that downward force pressure on the tail, times this moment arm. That has to, for this plane to fly level, has to enter this distance right here, the center of gravity moment arm, and we show it right here, right, times the weight of the airplane, the moment that produces, the force that produces. If the tail moment arm is greater than the center of gravity moment arm, the plane's pitching up. If the center of gravity moment is greater than the tail moment, then it's pitching down. And then we ask them about these. And what we're saying here is, hey, if you got a longer tail moment, what you're trying to get is, hey, you're changing this distance. And that has a big impact on the tail moment. Okay. Now I'm going to jump on back here. Let's put people back to this side. Do we have any questions? Just went through that pretty fast. Okay. I'm going to put somebody on the spot here. Let me see if everybody's paying attention. Of the 3 airplanes up there, which has the largest tail moment? All right, thanks. Kim's stepping up here. We'll take her. Go ahead, Kim.
I'm going to take a guess and say C.
You would be correct with that. Okay? That's exactly right. And it's just that distance then times the downward force of the lift produced to gives the total tail moment. Absolutely right. Thanks. Okay? So that's the lessons you're doing there. Now, how we do this experiment, just so out of curiosity, well, what do we have the kids do? Well, we actually have the kids go in and we change the center of gravity. We add some weight to the plane and we change the center of gravity. So what we end up changing is the center of gravity moment. And we just show them that if you change that distance, it impacts on how long and how well you can keep it level. And deflection is how much you're pulling back on the control. It's how much the elevator, goes up or down. So another way of thinking of that is when you pull back on the stick to maintain the airplane going up or push the stick forward in both instances you're trying to keep the airplane level. In one instant, you're pulling the nose back. In another instant, you're pushing the nose forward. And this all has to do with balance. Okay? And this is a nice tie-in with what you talked to them about in chapter 2 about how important it is that the airplane is properly balanced with weight and that load. Okay? So you have the kids fly. They'll do it. They'll go to settings. They want to know the center of gravity. You want to get that line. And then also the deflection for elevators will tell you in line 74. That's the data you're going to check. This one's a little bit different. All you do is look at the cockpit. You don't have to graph it. And then if you notice, we set the center of gravity negative 17 inches, which is pretty extreme. And we increase the payload a little bit there. And you can see it there. We do it once. We make the center of gravity minus 17.3, and then we go in the other direction at 22.1. It's only minus because we're changing the direction. It's not really negative. It's just we could have made this negative and that positive, but with default we say that's negative and that's positive on it. Okay? So that hits up lesson 6 for us. And it really drives home what moment and torque and all those good things are. All right. Back here to PowerPoint. All right. Now we get into lesson 7. And lesson 7, I'm going to blow this up a little bit more. Let me switch screens, swap displays. Lesson 7 gets into really much more into the engineering side. The tone's different. We're not making jokes about the title. Not that it's not that we want to be all that serious about engineering. I just wanted to kind of, okay, it's a little bit different now. It's a little bit older kid. It may be a little bit older kids too. And what we do on that, I don't know why wing loading keeps popping up. I will change this and it goes back and forth. But with the aspect ratio, what we're doing is, sorry, just see my upcoming screen's got wing loading. That's inappropriate. This next screen, I'll fix that next. But let's go back to aspect ratio and start again. The aspect ratio right here is the span to the chord on the plane. The chord is the width of the airplane. Just think of that. And it's the average chord. Because a lot, for some other reasons, the chord might change. What we do is say we're going to use the average. All right? And then we say to kids, hey, before we begin, we're going to do calculations. And we are, after all, engineers. We want to get the kids using math as a tool. We want it relevant. We don't want it contrived. You know? Kid says, well, why do you have me do this? I can do it immediately, or we're taking math to do math. No, we want to save you time. What we're trying to say is it has to have a certain aspect ratio between 1 and 12. If it's too low, it won't fly, and if it's too high, it doesn't come within the criteria we need. So the kids are going to divide this. Let me go ahead, go next. Go. So we're going to divide it right there from 6.25, 30.48. And again, in fact, it says this is important because we don't want to take off in a plane that won't fly, and we don't want to waste fuel and time. So say you know your criteria is for other reasons. You say, hey, we don't want an aspect ratio over 12. Then it takes time to sit down with a calculator back of an envelope and do a real quick check. And if you think about it, that's what engineering is. It's understanding the math, it's understanding the science, and then going out and designing something and building something using that math and science. I would even argue it's even better when you can do it from then, design something from scratch and you make it your own. We are doing electronics right now. I have the kids soldering, building a Simon Says circuit. They can program it, that Simon Says circuit. So when they learn the math and the science behind it, I taught them some electricity. That's all science, math, great. They started soldering. They built the thing. Okay, we're applying it. We can make it make music. I guess that's engineering. But really becomes engineering when they take that device and then figure out how to open and close their parents' garage door. Because now they understand it. They own it. All right? Same thing here. We want them to get it, so they design their own airplane. Now, here we go. So in this case is when they're going to start to actually go into Plane Maker. Plane Maker will be in the same folder as X-Plane. And that's where you want to go with this. We're going to give them a table, and it's going to work this way. You're going to be always copying the RV10. It's a van RV10. The reason we always copy the van RV10 is, the kids are going to change the wing. They're never going to remember to put it back. So make the RV10 your test mule. Have them copy it and rename it. And it can be simply, their first name, number 50 for aspect ratio. Or I'd say first name AR50. They would get the van RV10, go to save it, and then they'd save it with their first name, aspect ratio AR50, or their first name and the number 50. And I would do it with 40, 30, 20, 10. Have them just copy it right then. First time, they might not, it'll take them the first class to kind of get into why they're copying it, but they'll see in a moment. And then in the future lessons, they know to do it, and they just go fast with it. All right? So you're going to make these 50 copies in Plane Maker. Then they're also going to set in the data where they collect speed. Whoops. Hang on one second. All right. So right over here, they're going to go into, speed they're going to collect. That's annoying. And then distance and then landing gear vertical forces. All right, let's go up here. The thing, we're back in Plane Maker again, and we go in and we go ahead and just change the wings. So if you go into Plane Maker, you go under General, and then you can go under Wings. And under General, you can open up RV10, then you open up the plane, you go into Wings. And you go ahead and you change these things. Wing 1, and all you're doing is changing the semi-length. So in this case, it's going to be the RV50 airplane we opened up. Okay? Or no, our name 50, excuse me. Hopefully they haven't messed up the RV10. If they do, just copy it off the disk again, the RV10. Somebody will, sooner or later, kids mess it up. But anyways, there's a wing RV10. It's a 50-foot wingspan. We changed the semi-length to 25 feet. If you look down here, you can see the wingtip right there, the wing. Notice the wingtips aren't there anymore. That's because the whole wing itself has gone way out. The wingtips haven't moved with them. Well, we'll take care of that. Go to wing 2, change the lateral arm to this value, vertical arm, because you got to raise it up. It's in the worksheets. It tells them exactly where to put it in. Now, the kids can kind of figure it out too by trial and error, but we give it to you. So that way they get going on this. And they're going to repeat this then. They just did for the 50-foot airplane. I'll do it for the 40, the 30, the 20, the 10. Okay? Then they will go ahead and they'll practice taking off, landing, and what really gets to be, this is an opportunity to be talking about engineering trade-offs. Because what you're really saying to the kids is, okay, you go ahead and take off. If you go under about X plane, there's actually an AI. It'll take the plane off for them if they're struggling a little bit with their takeoff to get consistent values. Eric has actually had his son plot, I think, a scatter graph, and then had him then graph it and show why you would average things, that you know what the point is there, and that's something that we need to add. We still haven't. We've added some. Eric's made some really great suggestions in some earlier lessons. We need to add that lesson in there. All right. So with that in mind, you're going to have the kids put the wingtip in there. They're going to fly. They're going to take off. They're going to find out that their takeoff distance decreases by increasing the aspect ratio. Long, thin wings like this take right off. The plane will jump right off. And that's what's so exciting about using PlaneMaker. It's going to give you what really would happen. Now, the thing to ask the kids is, of course, and we have this and we ask these questions, and the teacher sheet has the answers, is, well, why doesn't every airplane have long, thin wings? You know, the kids got to think about, why wouldn't every airplane have long, thin wings? And so, well, and the answer to that is planes do different things. You have different functions, and based on those functions dictates how the plane is going to, the different functions are going to require the plane going to have different missions that are going to require different airplanes. There's also the cost issue on this. So let me explain it when I say different functions. If you are a race aircraft, you want to go as fast as you can possibly go. Lift is not a big concern. You got a big engine. It's going to pull you right through the air very, very quickly. So you're worried about drag. Well, long wings also give you drag, so you'll get rid of that. You might want to be more maneuverable. Fighter aircraft have short, stubby wings. Look at all the World War II airplanes. They had all short aspect ratios. You also get into the practical side. Fuel is stored on an airplane in those long wings. Well, if the wings can support the weight of the fuel, you can imagine at the base of the fuselage, you know, the fuel on the very end of that wingtip is acting like a lever, and that's a lot of weight. The way to think of that is, imagine putting 1 pound weights and holding them out, taking your hands from your waist down, holding the 1 pound weights up, bringing them up so they're at shoulder height on either hand. Now try doing that with 10 pound weights. Well, same thing on an airplane. So you'd have to really reinforce it. Well, that would drive up the expense. So what we're trying to get the kids to see is there's always trade-offs. Okay? So that's where we are with lesson 7 on aspect ratio. Another thing to tell the kids, frankly, is, guys, you are using a real tool that the engineers use. And I think that's exciting. The next lesson is wing loading, and really we're just going to say the plane's gross weight divided by the surface area of the wing. This is a very similar class form because, you know, they've been talking about weight, so they can go through 8 pretty well. Lesson 7 takes a period. This one will take a period because they're going to change the airplanes and fly them. Again, we talk about, we'll begin by using the most important tools of scientists and engineers, critical thinking and math. And we have them calculate the wing loading. Okay? And what they're going to find out is trade-offs again. If you have a high wing load, in other words, you've got a lot of weight compared, what we'll do is we'll change the weight of the aircraft, and then we'll see how that impacts in performance. And that's pretty straightforward. Well, what they find out real quickly, if you have a high wing loaded aircraft, you need a longer takeoff and landing distances. Low wing loading needs a shorter distance. You also have a higher stall speed if you're a high loaded plane. You also have greater flight performance, higher flight performance. You can also carry a greater payload. and a plane lower and lesser. So you can see that's a real vivid example of your trade-offs. Go out and look at the airplanes. You can almost tell by looking at them. And that's one thing we're going through down the road now with the kids, is showing them different airplanes and saying, what kind of airplane do you think it is? What is its mission? All right. Just went through aspect ratio and wing loading. Do we got it? Do we have any questions with that? Okay. You guys are a quick group. All right, let's go on to the next one here. It is 9 o'clock. The next one's power loading, and that's where we get into engine power. Okay. Let's just have a quick review of this. Let me see if I can get my pen down here. Command P. All right. What we do is talk about that thrust overcomes drag or pushes the aircraft along. So you're going to talk about several types of horsepower. Brake horsepower is the minimum you need. Okay, let me go ahead. Get this red again. I don't know why it defaults to white, but there we go. Brake horsepower right here. And in fact, I'll just do it this way. Brake horsepower requires the power equal. Brake horsepower equals the power to overcome drag. All right. So brake horsepower required equals the power to overcome the drag. How much horsepower do you need to just get over drag? Unfortunately, no system is 100% efficient. And so what you start to see is you've got to consider, hey, the propeller is about 80% efficient. So you need to take that brake horsepower and divide it by 0.8, which is going to be a larger number. So, and that would make sense because if you think about it, if I'm losing if I have 100 brake horsepower of 100 brakes horsepower of 100, oh man, let me try that again. Horsepower of 100. But if it goes through the prop, I'm only getting 80 because the prop is 80% efficient. And by the way, the Wright Brothers prop was pretty close to that, which is an amazing fact that we haven't really been able to. That's how a great job they did right off the bat. But if it's 80%, then I only put and I need 100 horsepower to get going, overcome drag. Well, if I put a 100 horsepower engine in there, I'm only going to have 80 horse. So I need to increase it. I need to divide 100 by 0.8. Now, the next thing is, if that's brake horsepower, this was thrust horsepower, then you have a concept called cruise horsepower. You don't ever want to run, besides when you take off in an airplane, you don't ever want to run full power. It's going to wear out your engine. So you want to take that thrust horsepower and divide that by 0.75. And it increases the number yet again. So there's 3 calculations the kids have to do. And in fact, we address that very fact to the kids in the next line down. If you see this, you may be thinking right now, wow, it takes 3 calculations just to find out how much power is needed to fly. I'm reading this right here. Whoops. Okay. Well, yes, engineering requires math. Not a math genius, just a solid foundation of math. You can do it. Then you can earn a lot of money doing cool work like designing and flying airplanes. We are very we talk a lot when I'm teaching this class about needing to do math. And with my seniors, I talk about the difficulty that the first 2 years of college are going to be. I think it's important. Don't send them to engineering school and they struggle and they flunk out because they didn't realize, wow, I'm going to have to be at a lab on a Thursday night. My friends are out going out. You're going to be, if you're majoring in some of these technical things, you are going to be at the library a lot and in labs. There's no getting around that. And I think you tell the kids that, then they know what they're getting in for. Because if they don't want to hear that, or they're not willing to do it now, then they're not going to get through the engineering side. So let's tell them that. But also tell them if they work hard, they can get there. And also on another minor point of this for the teachers here, applied math, the math degrees and the engineering degrees, they never got the memo for grade inflation. So for the high school teachers listening right now, and to middle school too, they can tell one of the kids, they're talking about colleges. We've had a problem with our kids going in the engineering program. They're there in their 2 or 3 years. They're getting there, but they get a C and they absolutely freak out. They think they're doomed. They've never gotten a C in their life. Well, you know what? I know for a fact applied math majors at University of North Carolina, their average graduating GPA was 2.87. I guess that's a B minus. So there are a lot of C's given out there. I don't know about the rest of you, but I saw bumper stickers that used to say, honk if you passed physical chemistry. Not get an A in it, just pass it. So remind your kids that. And math is one of those few things that you actually get better the older you get. All right, so we're looking at power loading. So you're going to have to do a couple calculations, and these calculations, by the way, affect not only that, but they also calculate your fuel consumption. So we have the kids do some calculations again. In every case of this, we try to use different calculations for the kids to get it. And there, it's gone there. So your math teacher friends, if you're teaching with co-teaching on your 7th grade team, your math teacher should like this stuff. And you can change this. Again, we're back in Plane Maker. And you can change the maximum allowable horsepower for your airplane. And that's where you go to change it. Now, do we have any questions on this? Because now you've done wing loading, aspect ratio, wing loading, power loading, stability, and flight controls. Now we're ready for the 10th lesson where they're going to get a chance to design the airplane. Well, with that in mind, here we go. Okay? This is the engineering design process. And what we talk to the kids about is your research, planning, prototype, production, new aircraft. I talk to kids about the difference between the scientific method and the engineering method. Okay? All right. In the planning method, research, we talked with the kids about research, and I'll get the lesson plan out here in a minute. We'll go through it, but you do research. The kids learn that, hey, a lot of times research comes from the marketing department telling you, hey, we think there's a need in this area. If we can build an airplane with these specs, we can serve that need. Or there's a new material that's come on, and we can now make our airplane fly better than anybody else and be more fuel efficient. So we talk to kids about planning, identify, brainstorm, select an idea, mathematically model it, do a test the idea, proof of concept. And one thing that's different than maybe in the scientific method is this iteration process. You build a prototype, test a prototype, make changes based on it, rebuild a new one. You stay internally. Whereas we know in science, propose a hypothesis, you test a hypothesis, then you let your peers duplicate it. And if your peers can't duplicate it, then we don't give you much credit. Engineering is much more internalized. The market's probably going to tell you if you have a good idea or not. So after that, we actually have the kids design your airplane. They're going to build it in plane, make it, and fly it next plane. But it's got to meet these requirements. 4-passenger airplane, each passenger can bring 20 pounds of luggage, 150 knot cruise speed, 800 nautical miles range. Okay? And what they start playing with is, and in fact, let me go ahead and go to this. Hang on one second. Let's bring this over here. Okay, so there's the research. It explains for the kids exactly what research might be. Then here's the planning and prototyping. And then there's the iterations that go on through here, production phase. You're trying to get the kids to come up with an airplane that can do all these things. And then they got to talk about fuel and change. All right? So what we need to do here is start off by looking at the average weight of the passengers and then how much luggage they carry. Then that gives you the average weight of passenger plus luggage is 190 pounds. We give you these answers in the teacher sheet. How many passengers will the plane be carrying, including the pilot? Total payload weight. So that gives us this. We calculate the gross airplane weight based on this total payload weight divided by 30%. These are rules of thumbs actually developed by a guy out of Penn who wrote a great book on airplane design. And that's what I used it based on. Okay, before I go on the next page, anybody got a question here? All right. Once we know that, gross airplane weight, we now can go and start deciding our wing. And honestly, the wing is the biggest bang for your buck. If you notice too, we don't do a lot with airfoil. There's some other programs that do airfoils, and that's great. It's one variable, but we think changing the shape of the wing is you get a lot more bang than just the airfoil. All right, so here you go. You've got gross airplane weight. That's what you just calculated. Answers there. And then standard wing loading is a value based on that, and it's 224 times, excuse me, the cube of the gross airplane weight minus 6. That value, the square root of that value of the gross airplane weight, the cube value minus 6 times 2.24. Then they have to decide, is it going to be a high wing loaded airplane or low wing loaded airplane? Really don't care which one it is. I care that just give me a good answer, reason why, that they thought through why it might be. Okay? Then we calculate the wing area. All right? So we calculate what kind of wing loading. Then we calculate, again, we bring the gross weight down. We know what that is. The wing load range, we just said that. High wing load range, low wing load range. We have a value for that. The wing area needs to be gross airplane divided by that wing loading area. Well, now we know the wing area. I tell them what the aspect ratio is. We just give that to them. And then they take the wing area they just calculated. They can calculate, if I know the wing area, then I can calculate the wingspan. If I know the wingspan, I can calculate the chord. Folks, I have 8th graders do this. They're fired up to do it. When they get going through it, they really get excited about what it should look like. Based on that, we start changing the horsepower. We do an assumption on horsepower, and we work our way, and we see what our fuel consumption is. So there's your brake horsepower. Thrust horsepower is going to be slightly larger than that. Thrust horsepower divided by the rate of horsepower is even going to be a bigger number. Then based on that, gross weight of the fuel, total fuel available, payload weight, we can start figuring out what kind of specs we're going to get out of there, what the nautical range is. Then they go to the last page here, fill out all this information, the gross weight, tells them where in the standard menu and plane maker it needs to be, wingspan, semi-length, chord, and now you've completed your airplane. Name it, test it, fly it. See how it does. And then for the kids that get ahead, and then there's some kids that just bust through this, get really fired up, have them make a 2-airplane plane with a pilot, give them a lot more thrust horsepower, and let them set the aspect ratio and go at it. And they'll see a much faster airplane. Not as fast as they think it'll be, but much faster. I just went through that pretty quick. I don't know if you necessarily followed every step of it. I'm not sure that's as important as you get a general sense of what we're trying to do here. I want the kids to use math, use the science they've already learned, use the math they're using now as a tool to help them design a plane, and they're using the software people actually use. And we use rules of thumbs that may not, if there's, aviation engineer, there's some things I'm sure I've said tonight make them cringe a little bit that are gross generalizations. But for what we're trying to do here, and that's really to get them to go through the engineering process, that's the reason we did it the way we did it. All right. That was a lot. Do we have any questions? All right. Go ahead, Kim.
Just a quick question. There's 10 lessons in this, correct?
Correct.
Okay. If we're meeting as a club after school every other week, and there's 10 lessons, and we're meeting about an hour every other week, how many lessons do you think we'll go through per club meeting?
I would say
I'm trying to figure out.
As a general,
I'm just trying to figure out if we'll have enough time to get through all of this and submit our airplane whenever the deadline date is.
Okay, deadline date won't be until the end is February 23rd. So I think you're going to have time. I would say most lessons are 1 hour in length. The 3 and 4 lessons 3 and 4 and 5 are shorter. 5 is very short. 5 is practice landing. So they get chances to practice doing that, And so I think if they practice, so to give your answer is that's roughly, let's say, 10 weeks. But having said that, they can do the contest. I think they can do some of those lessons quicker. And some of the stuff they can do at home too. They can do all the math calculations for, say, lesson 10. You could send that home and say, okay, I've showed you guys how to do this. Bring it back in and we'll start designing airplanes if you've done your math on this. Okay?
Okay, that works. Thanks.
All right. Yes, Eric. What's that?
Tom, can you hear me?
Yes, I can.
This is Eric in New Zealand. I've got a question. Do you have detailed reference on that one book you just mentioned that had the rule of thumb on the 30% loading?
Hang on, let me go to my library I'm calling out of and I'll get the book. All right, let me see here. Yes, this is from Skip Smith. It's the Illustrated Guide to Aerodynamics, and he's the one that did all the work on this. And he's a University of Pennsylvania, Penn State University. The guy's name's Illustrated Guide to Aerodynamics, H.C. Skip Smith. The book's getting a little more difficult because it's out of print. I've tried to contact him probably a half dozen times, but I think he's close to retired.
That's what Amazon is for.
Amen. I like the way you think. All right, let me go ahead and mute this. Any other things before I mute you, Eric?
Nope.
Okay, got it. We've got to get that in there. I would, it's on my to-do list, is to get all the books we used when developing this curriculum out there so people can look them up and make sure everybody's given the proper credit and all that good stuff. Anybody else have a question? Well, folks, it's 8:55. I'm not going to keep you just to keep you. If you've got any questions or something, please email me. I thank what you're doing, working with young people, and we're making engineers. David Taylor and I are working with kids at and after school and a homeschooling crowd, but outside of school crowd, I would say, because we got some kids that attend public schools during the day too. And we're teaching them engineering and have had a tremendous response. So there's a lot of people out there that are interested in this. And for Kim and other people too, if anybody's interested in robotics or bridges or Raspberry Pi or Arduinos, just let us know. We're doing all those things. I'm curious if anybody's doing a Raspberry Pi besides David Taylor that's on tonight. It's a computer it's a little tiny computer that's $35. You can program in Python with it and program in Scratch and do all these neat things with them. So those are nice compliments to Fly to Learn. I think if you end up teaching an engineering class, which I've been doing for 25 years, you want to do some flight, you want to do some robotics, you want to do some bridges, you want to do some electronics. Yes, biotech hacks come out, that things you can do in a lab that apply it. You're going to want to do that. I think that's how we get them interested, and we raise the bar from 3% of the people out there becoming engineers and trying to get, and technical people. Engineer to me is anything. It's a programmer, supply mathematician, it's a tool and die person, it's a CNC person, any of those things. If we want to get, instead of 3% of the people doing it and getting it to 15% of the people doing it, this is how we started. And on that note, if there's no other questions, thank you all very much for coming, and thanks for working with young people.